Hello, everybody. Glad to see you again. And let's start our lecture number 6 on astronomy. Okay. Today's lecture topic is light and telescope. Just looking through a telescope doesn't tell you much. A star looks like a point of light. A planet looks like a little disk. A galaxy looks like a hazy part. To use an astronomical telescope to learn about the universe, you must be able to analyze the light the telescope gave. Special instruments attached to the telescope makes it possible. But let's begin it from a short uh, intro video. It will be possible only to my physical lecture. Okay? The original image device in astronomy was the photographic plate. It could record images of faint objects in long time exposures and could be stored for later analysis. But photographic plates have been almost entirely replaced by electronic imaging systems. Most modern astronomers use charge-coupled devices, CCD, to record images. A CCD is a specialized computer chip containing roughly a million microscopic light detectors, arranged in an array about the size of a postage stamp. Also, CCD, or charge-coupled devices for astronomy, are extremely sensitive and therefore expensive. Less sophisticated CCDs are used in video and digital cameras. Not only can CCD chips replace photographic plates, but they have some dramatic advantages. They can detect both bright and faint objects in a single exposure, are much more sensitive than photographic plates, and can be read directly into a computer memory for later analysis. You can sharpen and enhance images from your digital camera because the image from a CCD is stored as a numbers of computer memory. Astronomers can also manipulate images to bring out otherwise invisible details. For example, astronomical images are often reproduced as negatives with the sky white and the stars dark. This makes the faint parts of the image easier to see. Astronomers can also produce false color images in which the colors represent different levels of intensity and are not related to the true colors of the object. You can see an example in this figure. In fact, false color images are common in many fields, such as medicine and meteorology. In the past, measurements of intensity and color were made using specialized light meters attached to a telescope on photographic plate. Today, nearly all such measurements are made more easily and more accurately with CCD images. To analyze light in detail, astronomers need to spread the light out according to wavelengths to form a spectrum, a task performed by a spectrograph. You can understand how this works if you imagine reproducing an experiment performed by Isaac Newton in 1666. Newton bored a small hole in the window shutter of his bedroom to admit a thin beam of sunlight. When he placed a prism in the beam, it sprayed the light into a beautiful spectrum that splashed across his bedroom wall. From this, Newton concluded that white light has made a mixture of all the colors. Light passing through a prism is bent at an angle that depends on its wavelength. Violet, or short wavelengths, bends more, red For long wavelengths, please spreading the white light into a spectrum, like in this picture. You could build a spectrograph with a prism to spread the light and a lens to guide the light into color. Nearly all modern spectrographs use a grating in place of a prism. A grating is a piece of glass with thousands of microscopic parallel grooves scribed onto its surface. Different wavelengths of light reflect from the grating at slightly different angles. So white light is spread into a spectrum. You have probably noticed this effect when you look at the closely spaced lines etched on a compact disc. As you tip the disc, different colors flash across its surface. You could build a modern spectrograph by using a high-quality grating to spread light into a spectrum, and a CCD camera to record the spectrum. The spectrum of an astronomical object can contain hundreds of spectral lines, dark or bright lines that cross the spectrum at specific wavelengths. The sun spectrum, for instance, contains hundreds of dark spectral lines produced by the atoms in the sun's spot gate. To measure the precise wavelengths of individual lines and identify the atoms that produce them, astronomers use a comparison spectrum as a calibration. Special bulbs built into the spectrograph produce bright lines given off by such atoms as thorium and argon or neon. The wavelengths of these spectral lines have been measured to high precision in the laboratory. So astronomers can use spectra of these light sources as guides to measure wavelengths and identify spectral lines in the spectrum of a star, galaxy, or planet. Because astronomers understand how light interacts with matter, a spectrum carries a tremendous amount of information, as you will see in the next lecture. And that makes a spectrograph the astronomer's most powerful instrument. An astronomer once remarked, "We don't know anything about an object till we get a spectrum." And that is only a slight exaggeration. Celestial objects, such as clouds of gas and erupting stars, emit radio energy, and astronomers on Earth can study such objects by observing at wavelengths in the radio beam. Where Earth's atmosphere is transparent to radio waves. You might think an erupting star would produce a strong radio signal, but the signals arriving on Earth are astonishingly weak, 1,000,000 to 1,000,000,000 times weaker than the signal from the FM radio station. Detecting such weak signals calls for highly sensitive equipment. A radio telescope usually consists of 4 parts: a dish reflector, an antenna, an amplifier, and a recorder. These components working together make it possible for astronomers to detect radio radiation from celestial objects. The dish reflector of a radio telescope, like the mirror of a reflective telescope, collects and focuses radiation. Because radio waves are much longer than light waves, the dish needs not to be as smooth as a mirror. Wire mesh with reflect all but the shortest wavelength radio waves. Through a radio telescope dish may be many meters in diameter. The antenna may be as small as your hand. Like the antenna on a TV set, its only function is to absorb the radio energy collected by the dish. Because the radio energy from celestial objects is so weak, it must be strongly amplified before it is recorded into computer memory. A single observation with a radio telescope measures the amount of radio energy coming from a specific point on the sky. But the intensity at one spot doesn't tell you much. So the radio telescope must be scanned over an object to produce a map of the radio intensity at different points. Because humans can't see radio waves, astronomers draw maps in which contours mark areas of similar radio intensity. You could compare such a radio map to a weather map showing contour field with color to indicate area of precipitation. A radio astronomer works under three handicaps: poor resolution, low intensity, and interference. Recall that the resolving power of an optical telescope depends on the diameter of the objective lens or mirror. It also depends on the wavelength of the radiation. At very long wavelengths, like those of radio waves, the diffraction fringes are very large, and the radio maps can't show fine detail. As with an optical telescope, there is no way to improve the resolving power without building a bigger telescope. Consequently, radio telescopes generally have large diameters to minimize the diffraction fringes. Even so, the resolving power of a radio telescope is not good. A dish 30 meters diameter receiving radiation with a wavelength of 21 centimeters has a resolving power of about half degrees. Such a radio telescope would be unable to detect any details in the sky smaller than the moon. Fortunately, radio astronomers can combine two or more radio telescopes to form a radio interferometer capable of much higher resolution. Just as in the case of optical interferometers, the radio astronomer combines signals from two or more widely separated dishes and pulls the waves into behaving as if they were collected by a much bigger radio telescope. The radio interferometer can be quite large. The very large array, VLA, consists of 27 dish antennas spread in a Y shape across the New Mexico desert in USA. In combination, they have the resolving power of a radio telescope 36 kilometers in diameter. The VLA can resolve details smaller than 1 second of arc. 8 new dishes antennas being added across New Mexico will give the VLA 10 times better resolving power. Another large radio interferometer, the very long baseline array, consists of a matched radio dishes spread from Hawaii to the Virgin Islands and has an effective diameter almost as large as Earth. Imagine this. The Allen telescope array, being built in California, USA, will eventually include 350 separate radio dishes. Radio astronomers are now planning the square kilometers array, which will contain a huge number of radio dishes, totaling a square kilometer of collecting area, and spread to a diameter of at least 6,000 kilometers. These huge radio interferometers depend on the state-of-the-art high-speed computers to combine signals and create radio imaging. The second handicap radio astronomers face is the low intensity of the radio signal. You learned earlier that the energy of a photon depends on its wavelength. Photons of radio energy have such long wavelengths that their individual energies are quite low. To get detectable signals focused on the antenna, the radio astronomer must build large collective areas, either as single large dishes of arrays of smaller dishes. The largest fully steerable radio telescope in the world is at the National Radio Astronomy Observatory in Great Bend, West Virginia, USA. The telescope has a reflecting surface 100 meters in diameter, big enough to hold an entire football field, and can be pointed anywhere in the sky. Its surface consists of 2004 computer-controlled panels that adjust to maintain the shape of the reflecting surface. The largest radio dish in the world is 300 meters in diameter. So large a dish can't be supported in the usual way. So it is built into a mountain valley in Arecibo, Puerto Rico. The reflecting dish is a thin metallic surface supported above the valley floor by cables attached near the rim. And the antenna fans above the dish on the cables from 3 towers built on the 3 mountain peaks that surrounding the valley. You may see it on a right corner in Figure B. By moving the antenna above the dish, radio astronomers can point the telescope at any object that passes within 20 degrees of the zenith as Earth rotates. Since completion in 1963, the telescope has been an international center of radio astronomy research. The third handicap the radio astronomer faces is interference. A radio telescope is an extremely sensitive radio receiver listening to faint radio signals. Such weak signals are easily drawn out of interference that includes everything from poorly designed transmitters in Earth satellites to automobiles with faulty ignition systems. A few narrow radio bands in the electromagnetic spectrum are reversed for radio astronomy. But even those are often contaminated by radio noise. To avoid interference, radio astronomers locate their telescopes as far from civilization as possible. Hidden deep in mountain valleys, they are able to listen to the sky protected from human-made radio noise. Building large radio telescopes in isolated locations is expensive, but 3 factors make it all worthwhile. First, and most important, a radio telescope can reveal where clouds of full hydrogen and other atoms and molecules are located. These hydrogen clouds are important because, for the one thing, they are the places where the stars are born. Large clouds of full hydrogen are completely invisible to normal telescopes because they produce no visible light of their own and reflect too little to be detected in photographs. However, full hydrogen emits a radio signal at the specific wavelength of 21 centimeters. You will see how the hydrogen produces these radiations in the discussion of the gas clouds in space. The only way astronomers can detect these clouds of hydrogen is with a radio telescope that receives the 21 centimeters radiation. Another reason radio telescopes are important is related to dust in space. Astronomers observing at visual wavelengths can't see though the dusty clouds in space. Light waves are so short they are scattered by the tiny dust grains and never get through the dust to reach optical telescopes on Earth. However, radio signals have wavelengths much longer than the diameters of the dust grains. So radio waves from far across the galaxy pass unhindered through the dust, giving radio astronomers an obscured view. Finally, radio telescopes are important because they can detect objects that are more luminous at radio wavelength than at visible wavelength. This includes intensely hot cars orbiting black holes. Some of the most violent events in the universe are detectable at radio wavelength. You have learned about the observations that ground-based telescopes can make through the two atmospheric mediums in the visible and radio part of the electromagnetic spectrum, right? Most of the rest of the electromagnetic radiation, infrared, ultraviolet, X-ray, and gamma ray, never reaches Earth's surface. It is absorbed high in Earth's atmosphere. To observe at this wavelength, telescope must go above the atmosphere. Named after Edwin Hubble, the astronomer who discovered the expansion of the universe, the Hubble Space Telescope is the most successful telescope ever to orbit Earth. It was launched in 1990 and contains 2.4 meters mirror with which it can absorb from the near infrared to the near ultraviolet. It is controlled from a research center on Earth and absorbs continuously. Nevertheless, there is time to complete only a fraction of the project proposed by astronomers from around the world. Most of the observations Hubble makes are at visual wavelength, so its greatest advantage in being above Earth's atmosphere is the lack of seeing distortion. It can detect fine detail and by concentrating light into sharp images can see faint objects. The telescope is as big as a large bus and has been visited a number of times by the space shuttle so that astronauts can maintain its equipment and install new cameras and spectrometers. Astronomers hope that it will last unit until it is replaced by the James Webb Space Telescope expected soon. The Webb telescope will carry a 6.5 meters mirror. Telescopes that observe in the far infrared must be protected from the heat and must get above Earth's absorbing atmosphere. They have limited lifetimes because they must carry coolant to chill their objects. The infrared astronomical satellite was a joint project of the United Kingdom, the United States, and the Netherlands. Infrared astronomical satellite, IRAS, was launched in January of 1983 and carried liquid helium coolant to keep its telescope cold. It made 250,000 observations and, for example, discovered disks of dust around stars where planets are now thought to have formed. Its coolant ran out after 300 days of observation. The most sophisticated of the infrared telescopes put in orbit, the Spitzer Space Telescope, is cooled to minus 269 centigrade. Launched in 2003, it observed from behind a sunscreen. In fact, it could not observe from Earth's orbit because Earth is so hot, so the telescope was sent into an orbit around the Sun that will carry it slowly away from Earth as its coolant is used up. Named after theoretical physicist Lyman Spitzer, it has made important discoveries concerning star formation, planets orbiting other stars, distant galaxies, and high-energy astrophysics refers to the use of X-ray and gamma-ray observation of the sky. Making such observations is difficult, but can reveal the secrets of processes such as the collapse of massive stars and eruption of supermassive black holes. The first astronomical satellite, Ariel 1, was launched by British astronomers in 1962 and made solar observations in the ultraviolet and X-ray part of the spectrum. Since then, many space telescopes have made high-energy observations from orbit. Some of these satellites have been general-purpose telescopes that can observe many different kinds of objects. Rosat, for example, was an X-ray observatory developed by an international consortium of European astronomers. Some space telescopes are designed to study a single problem or a single object. The Japanese satellite Hinode, for example, studied the sun continuously at visual, ultraviolet, and X-ray wavelengths. The largest X-ray telescope to date was launched in 1999. The Chandra X-ray Observatory orbits a third of the way to the moon and is named for the late Indian-American Nobel laureate Subrahmanyan Chandrasekhar, who was a pioneer in many branches of theoretical astronomy. Focusing X-rays is difficult because they penetrate into most mirrors. So astronomers devised cylindrical mirrors in which the X-ray reflect from the polished inside of the cylinders and form images on special detectors. The telescope has made important discoveries about everything from star formation to monster black holes in distant galaxies. One of the first gamma ray observatories was the Compton Gamma Ray Observatory, launched in 1991. It mapped the entire sky at gamma ray wavelength. The European Integral satellite was launched in 2002 and has been very productive in the study of violent eruptions of stars and black holes. The GLAST, Gamma Ray Large Area Space Telescope, launched in 2008, is capable of mapping large areas of the sky to high sensitivity. Modern astronomy has come to depend on observations that cover the entire electromagnetic spectrum. More orbiting space telescopes are planned that will be more versatile and more sensitive. All of the radiation you have read about in this lecture or listening about it has been electromagnetic radiation. But there is another form of energy raining down from space. And scientists aren't sure where it comes from. Cosmic rays are subatomic particles traveling through space at tremendous velocities. Almost no cosmic rays reach the ground, but they do smash gas atoms in the upper atmosphere, and fragments of those atoms shower down on your day and night over your entire life. These secondary cosmic rays are passing through you as you read your books or listening my lecture. Some cosmic rays can be down from high mountains or high-flying aircraft. But to study cosmic rays in detail, detectors must go into space. A number of cosmic ray detectors has been carried into orbit. But this area of astronomical research is just beginning to bear fruit. Astronomers can't be sure what produces cosmic rays, because they are atomic particles with electric charge. They are deflected by the magnetic field spread through our galaxy. And that means astronomers can't tell where they are coming from. The space between the stars is a glowing fog of cosmic rays. Some lower energy cosmic rays come from the sun, and observations show that at least some high energy cosmic rays are produced by the violet explosions of the dying star, and by supermassive black holes at the centers of the galaxy. At present, cosmic rays largely remain an exciting mystery. You will meet them again in the future lecture. Light is a visible form of electromagnetic radiation, an electric and magnetic disturbance that transports energy at the speed of light. The electromagnetic spectrum includes gamma rays, X-rays, ultraviolet radiation, visible light, infrared radiation, and radio waves. You can think of particles of light, a photon, as a bundle of waves that act sometimes as a particle and sometimes as a wave. The energy a photon carries depends on its wavelength. The wavelengths of visible light usually measured in nanometers. You remember? 10 in power 9 meters for angstrom. 10 in power minus 10 meters. Ranges from 400 nanometers to 700 nanometers. Radio and infrared radiation have longer wavelengths and carry less energy. X-ray, gamma ray, and ultraviolet radiation have shorter wavelengths and more energy. Frequency is the number of waves that pass a stationary point in 1 second. Wavelengths equal the speed of light divided by the frequency. Okay? Earth's atmosphere is transparent in only 2 atmospheric windows, visible light and radio. Atmospherical telescopes use a primary lens or mirror, also called an objective lens or mirror, to gaze the light and focus it into a small image, which can be magnified by an eyepiece. Short focal length lenses and mirrors must be more strongly carved and are more expensive to bring to shape. A reflecting telescope uses a lens to bend the light and focus it into an image. Because of chromatic aberration, refracting telescopes cannot bring all colors to the same focus, resulting in color fringes around the image. An achromatic lens partially corrects for this, but such lenses are expensive and cannot be made much larger than about 1 meter in diameter. Reflecting telescopes use a mirror to focus the light and are less expensive than refracting telescopes of the same diameter. Also, reflecting telescopes do not suffer from chromatic aberrations. Most large telescopes are reflectors. Light gathering power refers to the ability of a telescope to produce bright images. Resolving power refers to the ability of a telescope to resolve fine details. Diffraction fringes in the image limit the detail visible. Magnifying power, the ability to make an object look bigger, is less important because it can be changed by changing the eyepiece. Astronomers built observatories on remote, high mountains for 2 reasons. Turbulence in Earth's atmosphere blurs the image of an atmospheric astronomical telescope, a phenomenon that astronomers refer to as a scene. Atop of mountain, the air is steady and the scene is bad. Observatories are located far from cities to avoid light pollution. In reflecting telescopes, light first comes to a focus at the prime focus, but secondary mirrors can direct light to other focus locations, such as a Cassegrain focus or a Newtonian focus. The Schmidt-Cassegrain focus is popular for small telescopes. Because Earth rotates, telescopes must have a sidereal drive to follow the star. An equatorial mountain with a polar axis makes this possible, but alt-azimuth mountains are becoming more popular. Very large telescopes can be built with an active optics, maintaining the shape of floppy mirrors that are thin or in segments. Such thin mirrors weigh less, are easier to support, and cool faster at nightfall. High speed adaptive optics can monitor distortions caused by turbulence in Earth's atmosphere and partially cancel out the blurring caused by thin. Interferometry refers to the connecting two or more separate telescopes together to act as a single large telescope that has a resolution equivalent to that of a telescope as large in diameter as the separation between the telescopes. For many decades, astronomers used photographic plates to record images at the telescope. But modern electronic systems, such as the charge-coupled devices, CCD, have replaced photographic plates in most applications. Spectrographs using prisms or a grating spread starlight out according to wavelengths to form a spectrum, revealing hundreds of spectral lines produced by atoms in the object being studied. A comparison spectrum containing lines of known wavelengths allows astronomers to measure wavelengths in spectra of astronomical objects. Astronomers use radio telescope for three reasons. They can detect full hydrogen and other atoms and molecules in space. They can see through dust clouds that block visible light, and they can detect certain objects invisible at other wavelengths. Most radio telescopes contain a dish refractor, an antenna, an amplifier, and a data recorder. Such a telescope can record the intensity of the radio energy coming from a spot on the sky. Tons of small regions are used to produce radio maps. Because of the long wavelength, radio telescopes have very poor resolution, and astronomers often link separate radio telescopes together to form a radio interferometer capable of resolving much finer details. Earth's atmosphere absorbs gamma rays, X-rays, ultraviolet, and far infrared. To observe at these wavelengths, telescopes must be located in space. Those atmosphere distorts and blurs images. Telescopes in orbit are above the seen distortion and are limited only by diffraction in their orbit. Cosmic rays are not electromagnetic radiation. They are subatomic particles, such as electrons and photons, traveling at nearly the speed of light. They can best be studied from the above space atmosphere. Next lecture will be atoms and starlight. And for this moment, I think you enjoyed this lecture, and I'm looking forward to see you next time. Bye.